So in a very different spirit from the previous presentation, I'll be talking about how to qualitatively analyze nonlinear ordinary differential equations. So first, this is a sub-area of just generally studying dynamical systems. There's just any system whose state changes based on time and space. A classic example is the heat equation, which was mentioned earlier. However, these are very difficult to analyze and solve. And so I'll specifically be focusing on ordinary differential equations, which take this form, where you have some sort of time derivative of the state as a function of all the other state variables. And a famous example of one such system is the Lorentz equations. This is a particle whose the derivative of the state with respect to time is a function of the current position. And you get this very chaotic nature, which I will not get into in this presentation, but it's very neat. Okay, here is a very simple example where you have a heavily dampened spring. You can just hand wave away the second order terms just for demonstration. So something to note is that when x is equal to 0, so the origin point here, the time derivative is 0. And so we can think that a point there is not moving, it's stationary, it's fixed. But we're interested in analyzing what happens around in all of space, right? So what if we have a point where mu is 2 to the right of the origin? Then what will happen is that the time derivative is negative. So we can think of that like there's going to be a force towards the left, towards the origin. Now if we instead nudge the point to the left, and so it's on the negative x-axis, then the time derivative is positive, and it's going to be nudged to the right. So we see that any perturbation of the origin leads back to itself as during the infinite time horizon. And so we can classify that as a stable fixed point. In contrast, if you have a negative mu, if you push the origin towards the right, the time derivative becomes positive and it shoots off to positive infinity. In contrast, if you perturb it to the left, the time derivative is negative and it shoots off to negative infinity. So while it's fixed at 0, any perturbation causes it to go off to infinity in either direction, and thus it is an unstable point. Why is this useful? So in this case, it's very simple to find an analytical answer. You just integrate very easily. However, these tools do apply to much more complicated situations where you can't quite have an analytical solution to the problem. So if there's several higher order terms in your differential equation, in the one-dimensional case, you can linearize it. So we take a very similar approach here. You can think of it like zooming in. Very close to a fixed point where it looks linear. And so we define a perturbation as just eta of t equaling x of t minus the critical point x star. You take the derivative and you find out that this is just f of the critical point plus eta, the perturbation. You do a Taylor series expansion to f, which is just the function governing your ordinary differential equation. By definition, f of x star is just 0 because it's a fixed point. The time derivative is 0 there. And then we'll just, since the linear term dominates, we can ignore the higher order terms. And so eta dot is approximately equal to eta times f prime of x star. Since this is a constant, this looks very similar to the dampened spring example. If you're familiar with differential equations, this will give you an exponential answer. So the way we interpret this is that all we need to do is find the sign of f prime of the critical point. If this is negative, the way we can interpret that is that any perturbation decays. So that fixed point is thus stable. If this is positive, then all perturbations grow exponentially. And so that fixed point would be unstable. Now, this is very useful in most circumstances. However, there are some edge cases, such as when f prime is equal to 0, where you do need those higher order terms in order to analyze the behavior there. But for a lot of situations, this works well. So in most physical situations, you have parameters, such as, again, like the spring. You have a physical parameter that may or may not change the qualitative behavior of your system. So in this example, ODE, you have r plus x squared. When r is negative, you have two different fixed points. The one on the left is stable because, again, you have that negative slope, so perturbations decay exponentially. On the right, you have an unstable point because of the positive slope there. As we increase r, though, once it reaches 0, we have this interesting fixed point here. Because to the left of it, it's positive, so we expect the point to be nudged to the origin. And at the origin, it's fixed, but if we perturb it to the right, it's also going to increase to the right. And so that'll shoot off to positive infinity. And this is called a transient point, since it's like semi-stable. Here, with when we keep increasing r, then there's no fixed points. And so any point will just shoot off to infinity. And so we can summarize this behavior in terms of a bifurcation diagram where we plot the parameter on the x-axis and then the fixed points on the y-axis. And here, this stable branch corresponds to the left fixed point, stable point, and then this unstable branch corresponds to the right unstable fixed point. And there's actually a lot more of these guys. Here we have a transcritical bifurcation where we see like an exchange of stability occurring. Here we have a supercritical pitchfork bifurcation, where when the parameter is negative, you have this one very stable branch. However, once r is positive, the solutions tend to gravitate towards these two stable branches and away from the origin here. And then for the subcritical pitchfork case, you kind of have the opposite going on, where it's unstable when r is positive, and if it's outside this region, it'll blast off to the negative and positive infinity, but if it's within this region, it'll tend down to the 0. Okay, 2D systems. Now this is the proper equation for a spring, and now we have some more tools that we can use to analyze these situations. So we can actually turn this into a linear system of ordinary differential equations by making this substitution of x dot equals just velocity, and then the derivative of velocity is just acceleration, and then we can write this in matrix form, and we have these linear coefficients. So as it turns out, there's a very similar test for stability as with the one-dimensional case, except instead of analyzing the derivative, you analyze the Jacobian. What we can use is the eigenvalues of said Jacobian. In this case, since it's linear, we just need to analyze the eigenvalues of this matrix right here. So just like in the case of the one dimension, if it's positive, that would indicate that the vectors will explode to infinity along the eigenvector associated with the positive eigenvalue. If both are negative, such as in this case, then we expect the point to be stable along those eigenvectors associated with those negative eigenvalues. In this case, you have two negative eigenvalues, and so this fixed point will be stable as solutions tend to gravitate towards it. In the spring example, if we don't have dampening, then you would expect the spring to just go back and forth, right? And if you compute the eigenvalues of this when b is 0, you'll get two complex numbers. And that corresponds to a center. So like orbiting around, and that makes sense because you have this, you have this rotation going on with a undampened spring. However, if you do have this dampening term, you will expect this sort of spiraling. That corresponds to having a negative real value with the eigenvalues. And there are several more cases of this. And since the way you compute the eigenvalues is based on the determinant and trace, in the 2D case, we can summarize all the qualitative behavior via just the determinant and trace. Saddle points correspond to having a positive and negative eigenvalue. Let me draw one up here. So on your stable axis, maybe you have it shoot off because the eigenvalue is positive, but then on this other axis, you have it gravitate towards the center. And so a solutions outside of this will tend to look like this. And then you have spirals. Again, stable spirals are those that spiral inwards. Unstable spirals spiral outwards. And that corresponds to the real portion of your eigenvalues. And you have stable nodes and unstable nodes. So if they shoot inwards towards the fixed point or away. And there's several edge cases. So like with the one-dimensional case, if we have higher order terms, what we can do, we can linearize it around the said fixed points. And we find that we can write the equation like this in terms of the Jacobian evaluated at the fixed point plus quadratic terms. And it turns out that the prediction for the linearized system, that is if we just focus on the Jacobian there, whatever we predict out of that applies to the original system, if it's a saddle node or spiral. However, there are edge cases such as stars, degenerate nodes, non-isolated fixed points, and centers, where higher order terms can mess that up, and so you have to be more careful around those. But for the most part, it seems that we can just linearize the system, find the Jacobian, compute the eigenvalues, and then we have a good idea of what is occurring with the differential equation. And again, we have, just like in the one-dimensional case, we have bifurcations. So one trivial way to extend it to 2 dimensions is just having this y dot equals negative y. And so we get the transcritical, supercritical, subcritical bifurcations. This depicts the supercritical case, and as you can see with the y-axis, they all tend towards the x-axis. And again, depending on the choice of mu, we see that behavior reflected, as in with one-dimensional supercritical case. A more involved example is the hot bifurcation, where this looks kind of nasty, but you can turn it into polar coordinates and you get this really nice form here. And this looks identical to the supercritical case. And so what we expect is that when mu is negative, we expect R to tend towards 0. And so we can think of that as a sink. So it spirals inwards towards 0. Then if mu is positive though, R is going to want to go away into this outer surface here. Or if it's outside of that, it'll tend towards the surface. And so that's called the limit cycle, where it limits towards a particular orbit, which depends on the parameter mu. Okay, so now we have a good amount of tools to analyze a physical system. And this is a historical example of analyzing the oscillations of a fluid through a pipe. And Holmes talks about, in the 70s, talked about how you can turn this from a PDE to an ODE, and that way we can use the tools we have to analyze it. So here, this is very nasty looking. There's some constants here that are not included for clarity, but the coefficients of this matrix are dependent on the physical parameters of the system. And the two of interest are this rho and gamma. Rho corresponds to the velocity of the fluid, but gamma depends on other parameters, which I don't know what they exactly depend on. Holmes computed that these are the fixed points. When this lowercase gamma is 0, that corresponds to ignoring gravitational effects, and you have these 4 outer points in the trivial fixed point in the middle, and then if gamma is non-zero, then they get shifted a little. So now we compute the eigenvalues. In this case, we'll focus primarily just on the origin here. And so when we compute the Jacobian and then compute the, try to find the eigenvalues, we get some interesting behavior. So the equation for the eigenvalues can be written out like this. It has to be done numerically because these equations are very large and disgusting. But what we can do is notice that if A0 is equal to 0, then one of these eigenvalues will be 0. And from our previous qualitative analysis, an eigenvalue of 0 seems very odd. It's neither positive nor negative nor complex, so it'll be weird to work with that. A0 being equal to 0 corresponds to these two curves, BS1 and BS2, and that divides the space into 3 separate regions. Holmes numerically determined that in region 1, all the eigenvalues are negative, so that corresponds to a stable sink at the origin. 2, you have 1 positive eigenvalue and 3 negative. That corresponds to some sort of saddle point. And in region 3, you have 2 positive and 2 negative eigenvalues. So that again corresponds to some sort of saddle point. Now, some interesting behavior occurs when you cross these boundaries. And that is something Holmes tried to understand more. So this summarizes the behavior at the fixed points. As you can see in region 1, you get that sink behavior. And region 2 and region 3, again, you have some saddle point behavior going on. But when you cross this region, what we can actually do, we can actually reduce the dimensionality of the problem and analyze it along its manifold. And I'm running out of time here, so I need to speed run this. But essentially, you can split up your different eigenvalues, your different vectors into different buckets. You have the stable directions, the unstable directions, and then your center manifold. And in this example, for example, you have a stable manifold and then your center manifold. So along the stable manifold, all solutions will go quickly towards the center manifold. And so if we understand the dynamics of the center manifold, we can have a good qualitative understanding of the rest of the system. So to find said center manifold, in the 2-dimensional case, we have these 2 equations. We just say that the center manifold is a function of x, and then that gives us 2 equations. This just comes from that, and this comes from just taking the derivative of h of x with respect to t. We say that h of x is a Taylor series, and we just find its coefficients. That gives us the equation of the center manifold. And here, for example, you have this vertical stable manifold, and they all converge to this center manifold here. And you can see that we can use our previous tools to find the behavior of that center manifold. In this case, you have solutions that go off this way and towards this fixed point. So back to this solution, since only one eigenvalue is 0, we have buckets with 3 terms, stable and unstable, and then we have the one with 0. And so we can focus all of our attention on that center manifold, which has a dimension of 1, and we already know how to analyze a one-dimensional system. So we can just apply those tools here, and it massively simplifies our problem. And hopefully that demonstrates the utility in qualitatively analyzing differential equations and the different tools you can use for that. Are there any questions? Yeah?
So you go back to like one of the first ones where you derive like the first slides where you derive like the f prime at the fixed point, like even earlier. Yeah, that one.
Uh-huh.
So this is like determining whether or not you have a fixed point and like the behavior immediately around that, just using like a first order linear approximation.
Exactly. Yeah.
So then is it interesting to talk about just 1 degree higher, like the Hessian matrix? Can that be like computed in any case, or?
I don't.
Does that give you information?
For those edge cases, it is useful, but the linear dominates in most situations. So again, like with saddle nodes and spirals, the Jacobian is sufficient for those.
Sure.
But where you do need the Hessian and whatnot is for these other cases where those where the Jacobian, yeah.
So that becomes important for them.
Exactly.
Okay.
Any other questions?
Yeah. So what's the stars? So like I guess.
Yeah, the stars, if I remember correctly, it just kind of shoots outwards or inwards. Is that right, Ryan?
Yeah, I think it's when all the eigenvalues are the same.
Yeah.
And
then
and what's degenerate about,
yeah.
or what's degenerate about?
Degenerate, you have something weird going on where it's like almost a spiral but not quite. It's like this is similar to like an overdamped spring.
Yeah, I think what's weird about it is that you could have either of those if you have all of the same eigenvalues. And so you don't necessarily know which one you're at or something. They could switch between them.
If you're all, I don't say you should start it. Unless it's
Not necessarily. It depends on the system, which again is why the Jacobian alone isn't sufficient for those.
Yeah.
Oh yeah, yeah. Okay.
Cool. Thank you.
Okay, thanks, Jared.